Hi everyone, welcome to Under the Microscope. I am your host, Pranoti, and today we have with us a very interesting guest. Her name is Áine Coogan, and Áine is a materials chemistry PhD researcher at the Trinity College Dublin, which is in Ireland. Yes, it is in Ireland. So, hi Áine, how are you?
I'm good, how are you?
I'm good. Did I pronounce your name correctly? I want to make sure I pronounce your name correctly.
You did indeed, yeah.
I did? Okay,
Good job.
super. Oh, thank you. Super. So I know a little bit about your research because we just spoke about it, but tell me, please explain your research to me in super simple words.
Okay, so I'm a materials chemist. So basically what that means is I'm kind of on more the nano materials side. So super small materials, 1 billion times smaller than a meter. And I usually work with two-dimensional materials, usually just called 2D materials. And essentially what they are is like if you took a piece of paper and made that nano. So they're as thin as you can imagine, very often as thin as an atom or a couple of atoms thick. And they can possess really interesting properties just because of how thin they are and how small they are. So the class of materials that I usually work on is called a layered double hydroxide, and there's thousands of different combinations of them you can make, and you can use them basically to tailor to different applications, which is quite cool because you can play around with a lot of different applications just with this one class of material.
Oh wow, that sounds super. I have so many questions. Okay, first things first. You mentioned a billionth of a meter or kilometer, was it?
Yeah, so nanometer is a billionth of a meter. So
a billionth of a meter.
Yeah, so if you think of like a hair, I think that's kind of the example that everyone gives. Every nanoscientist gives the human hair example, but a human hair, I think, is something like 80,000 nanometers thick. And you think of how thin a hair is. The scales we would be operating on is between 10 to 100 nanometers, so tiny.
Okay, yeah. Interesting. Yes, I know I'm aware of the human hair or the paper or like atomic level and all of that, but I just had this crazy idea. If you can explain the scale or the small scale of nanomaterials from the dimensions perspective. I just looked up the world population and it is 7.9 billion as of 2 years ago. So let's go with 8 billion to make it easier. Mm-hmm. So if there are 8 billion people on the face of Earth, then nanoscience would be 8 out of these 8 billion people. That would be 8 nanometers.
Yeah, I guess so. Yeah, it's an interesting way of looking at it. But yeah, I think it's a billionth. It's 10 to the 9 anyway. So
10 to the 9, exactly.
Yeah.
Yes. Okay.
So yeah, it'd be 8 of those people would be what you're focusing on, I guess. Yeah.
That's the scale. That's the scale. And these 8, not people, but these very, that is so cool. Oh my God. I'm so proud of myself for coming up with this idea. Because I always find it difficult to explain to people. I mean, it makes sense, like 10 to the power minus 9 meters. That's what nanoscience, nanomaterials are. Nanoscale is that level, but it's not. I've realized that for people who are not in the field, for them, it's like, yeah, whatever, 10 to the power of 9. But it's like 10 to the power of minus 9, dude.
It's so hard to put it into context when you don't, like, when you work with it every day, it's kind of, oh, whatever, that's how small it is. But when you try and explain it to someone, they're just like, but how can you use it if it's that small? And it's like, there's ways around it, you know. It's hard to put it into context when you don't really work with it every day. Yeah.
Absolutely. So you mentioned, that you are working with these nanomaterials and you are tweaking their properties and you're playing with them, so to say. So what kind of instruments do you use? Give me your top 5 favorite scientific instruments or toys. Instruments.
Top 5. Most used or the ones I like the most?
The ones you like the most.
The ones I like the most. Well, I love the transmission electron microscope, the TEM. I don't use it personally. I have like collaborators that do my TEM for me, but I do use the scanning electron microscope. So I use that quite a lot, which is awesome. So instead of like your normal microscope, you're shooting electrons at it so you can see smaller feature sizes. It's really cool. So I like that a lot. It is scary because it's like this big, massive microscope that takes up an entire room. But yeah, I love that. And then X-ray diffraction is kind of like, it's boring, but it's so nice at the same time. You know, you get so much information out of material. UV-Vis, which is like just the absorption spectroscopy, I have to use it every single day. So I kind of have a love for it, even though it seems to be the most boring thing in the world. I just love seeing those peaks, and like you get your exciton peak, or you get like you're looking at a dye and you know the peak is exactly where it should be. So I kind of like the simplicity of it a little bit. Circular dichroism is a technique that I use a lot, which I can talk about a little bit more, but it's kind of like, it's a type of absorption spectroscopy. So if you imagine your UV-Vis, so you're just shining UV invisible light through, it's the same as that, but instead the light is polarized. So you can see if your material absorbs left-handed or right-handed light more. So I love that. Our machine's very old, so I don't love her, but I love the technique.
Okay.
Yeah.
Okay. Light has two wave patterns, and polarized is the one. Okay. Through this filter, now you're shooting at your samples only either with this or either with this, right? So
yeah, exactly. So
yeah,
so that would be linearly polarized, but you can also have circularly polarized light. So instead of the wave just going this way, it kind of goes in a helix. That's what we work with. It's I don't fully understand how it's a series of half wave, quarter wave plates. It's more of a physics thing, is how the light gets generated, and then that's what we're actually seeing our sample absorb. Yeah.
Oh my God. So you're like drilling into the substrate, or is it like more of a coil that is hitting the substrate in the helical?
Oh, so it's just the light. The light is just how the waveform has that form. So it's polarized circularly rather than just in a line. Yeah.
Oh
it's still traveling in that direction, but it's
okay.
Essentially.
I need to ask ChatGPT how this works, or I can ask any of our previous guests who have physics back. Oh my God, this is so cool. This is so cool. Okay. I love all the instruments that you mentioned, especially the scanning electron microscope, because I used to use that a lot during my master's and my PhD work, and I love it. And I also see what you mean with the XRD and the UV-Vis, that it looks boring, but if you understand the data, it's like abundance of information. So
yeah, you get this tiny little peak that's not, it's like someone will be like, oh, what's that? And it's like, oh, that's my product, that's what I want. You know, it seems so boring to someone who doesn't use it, but when you finally get that after weeks or months of trying, you're like, yes, okay,
yes,
I'm on the right track. Even though it's tiny, it's there. I can keep on building on that. Yeah,
absolutely. Awesome. So Áine, tell me about your journey so far. So how did you end up almost finishing your PhD in materials chemistry at Trinity College Dublin? How did that happen? Take me through the journey of Áine, the story of Áine.
Absolutely. So in school, I was kind of not interested in anything other than science. It was kind of, I knew that's what I was going to do. So in Ireland, when you do your leaving certificate, you have to do English, Irish, and maths, and then you pick 4 subjects. Some people pick 5, some people pick 3. You only have to do 6, but most people do 7 in total. So I picked biology, chemistry, physics, and then French, because a lot of universities need you to take a language, which I never kept on, but I'm not very good at it. But so I kind of knew, I just did biology because our school didn't offer any other science subjects. So some schools offer applied maths, which is more kind of mechanics. I went to an all-girls school. It's a bit rare for those kind of subjects to be offered. So I knew that physics, chemistry was kind of the route I wanted to go down. I was pretty sure about that. And I was looking into if there was any joint honours courses in Ireland where you could do equal parts physics and chemistry, and there wasn't. But then I came across the nanoscience course, which is physics and chemistry of advanced materials. So it's kind of 40% physics, 40% chemistry, and then 20% maths. And I was like, yeah, that's awesome. And then I looked into what nanomaterials are, and I was like, okay, yeah, this is cool. So it is kind of a unique course in that it's probably one of the more like specialized courses, I guess, to do in undergrad. It's usually you go into more of a general science, or you just go into general chemistry, general physics, and then you specialize after that. So even though it seemed specialized, it was still very general. Like we shared most of our lectures with physics, with chemistry, and with other sciences as well. So it was nice. We had a very small course, but we were still mixed in with 200, 300 other people between the physics, chemistry, and biology side of things. So that was my 4-year bachelor's. And in the final year, you have to do a 3-month kind of placement, research placement. So you can opt to do that in the university with a professor, or you can do it abroad. And there was a professor that had taught us that I was really interested in his work. So I kind of had a chat with him, and he ended up having a project in that year. So I did the project with him. And then a month into that project, I was like, I want to do a PhD. How can I do a PhD? So we started looking at grants and stuff like that. So we applied for a grant together and then got that. So that's where I am now. Still in the same group. Yeah, so it's 8 years now in Trinity, which is a long time to be in one place, but yeah.
Well, I mean, if it works, it works, and this is amazing. So which grant do you want to thank your grant folks for?
Absolutely, of course. So I'm funded by the Irish Research Council. So I've an Irish Research Council postgraduate scholarship. It's all thanks to them, I guess, that I'm able to do what I like doing every day.
That is so cool. I love it. It's just so cool. So if I were to ask you because materials chemistry is quite a broad topic, right? It can be any and everything, literally, because materials are everywhere, and where there is material, there has to be chemistry. So which niche of chemistry are you in? You're definitely not textile materials chemistry. You're definitely not wood chemistry or whatever. So this is like a stupid question that I'm asking you, hoping that you can give me a very simple answer.
It's kind of, I guess, which is also an entirely massively broad field. It's more so inorganic chemistry.
Okay.
On the nano scale. It's like the actual techniques we use to make them are just really simple inorganic chemistry techniques. There's no crazy lasers being used or anything. It's just really simple synthetic methods. So it is, it's all inorganic materials that I use. The occasional organic material to stabilize it or something, but it's just inorganic. So metals, and then occasionally some other elements like boron and nitrogen and that kind of stuff. Yeah. Okay, that's interesting. That is very interesting. So inorganic materials chemistry, in the 2D space, so 2-dimensional material space. Okay, great. So where can these materials or these techniques that you're working on, where can these be applied? And I realize that maybe the research is very much on the basic side. Maybe this is just my assumption. Would it be to get our electronics run faster, or like solar cells? Like, where can your materials be applied? So the ones I work with specifically have a couple of different applications. Like in general, inorganic materials are everywhere. So they are used in solar cells, in tandem with organic materials as well. They're used like the likes of graphene and transition metal dichalcogenides, which are another very common class of 2D materials, are used pretty often and are being integrated more and more into electronics. But my stuff is I do focus on 3 different kind of applications. So the main one that we're focusing on at the moment, that we're kind of finishing up that project, is for water purification technology, and also for catalysis, so speeding up a reaction to form a product. And then another one, which is a little bit more kind of vague and kind of a harder concept to get your head around, is chirality, which is kind of more on the biomedical side of things. So I can use the same material and tailor it for those different applications, basically. So they are actually quite diverse in the applications they can have. Which is really neat.
Yeah, absolutely. This is amazing. So you mentioned water purification. Is it because I was recently made aware that there is a field called green chemistry, which is about reducing the amount of waste you create during your research from
Mhm.
the solutions, materials, all that kind of point of view, substrates, everything point of view. And one of the main aspects of it is, of course, try to limit the amount of waste you create, but also whatever waste you create, try to purify it or reuse it. So is the when you say water purification, is it more along those lines, or is it more along the lines of, okay, this is my glass of water that is purified through a filter?
It's more so kind of the purification for like a consumer, so like a water filter. But we have been wanting to kind of test, okay, how clean our water is by trying to do a nanomaterial synthesis in the water and seeing if you get impurities and, you know, defects and all that kind of stuff. Because that would make the process, it's already quite a green process, but it would just make it that much cleaner that you're constantly reusing the same batch of water. So we have wanted to try that. But it's just not something we've gotten around to yet. But yeah, it's more so on the like, yeah, you
Consumers.
have your glass of water, you're not sure if it's clean, you pass it through a filter, that kind of thing. Yeah.
Okay. Oh my God, this sounds so cool. Oh my God, oh my God, oh my God. Okay, so the next question I have for you, this is like I know it's a mean question and I apologize in advance, but if you have to pick one research project or experiment that you're most proud of, or the most fun or quirky, like super cool, can you pick one project and explain it to me in simple words in the section we call In Other Words?
Yeah. So I think I'm kind of in two minds between this because the one I'm most proud of is very boring on a day-to-day basis, but it's very important. So, and I am very proud of the work that's been done. So I think I'll talk about that one because it's probably a little bit easier to break down as well. So that project is to do with this water purification that I've been talking about. So what we do is we use the 2D materials to make essentially like a Brita filter, like the filter that you would have in your house to purify your tap water. And some work that was done in the group beforehand that I kind of had a little role in was kind of optimizing these filters. So what we do is we have the 2D materials and you basically just run it through a filter, have a little substrate, and then that creates these little tiny channels that all of the contaminants get blocked in, basically. So the sheets kind of all stack on top of each other like this, and then there's little tiny holes and pores that the water travels through, and as it travels through, those contaminants get blocked. So we can basically block stuff down to like 2 or 3 nanometers in size, so like molecules, individual molecules. So we usually work with dyes because it's really easy to see. You pass something that's bright pink through it and your clear water comes out the other side. But we do want to work on other kind of organic stuff as well. That's pretty common in wastewater, but dyes are a major contaminant in wastewater anyway, especially close to textile factories and stuff like that. There is a lot of a lot of it is leached into the water. As much as they do try to clean it, there's only so much of it they can get out. So that project was pretty successful. Like we can retain up to 100% of the dyes in these little membranes. They're very cheap to make. But the problem was they weren't really sustainable because you use it once and then you have to throw it out because it gets clogged, basically. So no more water can get through. So then a kind of continuation of that project was trying to figure out ways to get the dye out. So the first thing we thought about was just putting the membrane into an oven and burning the dye off. But that's not very sustainable, right? You can do it, but you have to put it up to 400 degrees and then it's burning it off. So, not the best. And also you can get some changes in your material. You don't really know what's happening. So instead, that's where those layered double hydroxides that I was talking about earlier, that's where they come in. So they can be, depending on what elements you have in there. So the ones we mainly use are copper and aluminium, and they can be semiconducting. So what that means, there's basically an energy gap, and when light of a certain wavelength hits it, you can get an electron excited from the valence band to the conduction band. So it basically is a good light harvester. And that's one of the common things that you need for a photocatalyst. So catalyst drives a reaction. A photocatalyst will drive that reaction using light. So we thought, could we use these in the membranes to promote the catalysis of the dye that's in the membrane to get rid of the dye, and then you have your material back from scratch. So we tried that, and it does actually work incredibly well. And our light source, because we're not like a fantastically funded lab, we're doing okay, but we don't have crazy multi-million euro equipment or anything. So we bought a little LED lamp from Lidl. It's like a 5-watt LED or something. Like, it works really well and it's really cheap. Sunlight obviously does the best job, but for basically repeating the same experiment every day, and I live in Ireland, so the sun doesn't always shine very well, so we needed a cheap LED to test it with. And so we basically just put a little bit of hydrogen peroxide in there, a tiny amount, some water, and then just shine a light on it, and then over the course of about 2 hours you can see that the dye disappears, and then you get your material back from scratch. So
that is so cool. Okay. So the project was about how to make the filters or membranes more efficient or more improved,
more reusable.
Yeah. Okay, that was, oh wow, that is so cool. Is this the project that you were referring to where the paper was published very recently?
Yeah, the paper was published like a week and a half ago. It was probably like 2 years in the making, a lot of work, a lot of undergrad students helping us out with it and stuff as well. There's a lot of people on board to push it over the line, and so it's really exciting. We're still not quite at the stage where the device is reusable, but the material is, so we can basically like redisperse it, put it on another template, and we can keep on reusing the material. But we need, the next step is to make it more stable so we can actually use the membrane over and over again.
Right.
But it's a good first step. Yeah.
Absolutely. Congratulations. And it's about like transferring the technology from the lab bench to the production line or to the market shelf. That's what needs to be done. That is so cool. That is, oh, congratulations. Where did you publish the paper?
In the Journal of Materials Chemistry A. Yeah, very, very excited about that. I'm very happy with that. Yeah.
That's a big one. Congratulations to the
Thank you.
entire team. That is so cool. And would you like to share with our listeners and our viewers about how you used AI, ChatGPT, to support you in the publishing process? Let's put it that way.
Yeah, absolutely. Yeah, I know there's a lot of chat about using AI. My AI did not write my paper. Don't worry about that. Got a round of revisions back. So we submitted the paper, came back with major revisions, which some of them we could address pretty easily. There was one in particular that was kind of vital for the paper, but we just didn't have access to the equipment, but it needed to be addressed. It was a major kind of overarching question of the paper that we hadn't answered. So I couldn't find anywhere online of any way to work around this. I chatted to my supervisor, he wasn't sure. So I basically copied the reviewer's point into ChatGPT and said, we don't have access to this equipment. Can you provide me with an alternative experiment? And I had to word it a couple of ways until I got an answer. But I did eventually get a couple of answers and I checked them. One of them was completely valid. We tested it, it worked, and the reviewer was happy with it, and no more corrections required, accepted straight away after those major revisions were applied. So that was, I would have never been able to, like, the paper probably wouldn't have been published there otherwise. We probably would have had to pull it and submit to maybe a lower impact journal or something, because it was a question that this was the only way it could be answered and we couldn't think of another way. So that was actually, yeah. So it can be used to your advantage if you use it correctly and ethically, and
Absolutely. Yeah. Can you tell us what the question was, or will you tell me after we stop recording?
I can tell you, yeah. So it was basically, they were asking about the mechanism of the catalysis. So we had proposed that it was something based on other experiments, and he was just like, yeah, like it's pretty commonly known that that's it, but you need to prove it for your own system. So he just wanted us to prove that certain free radicals were being produced. Mm-hmm. And he asked us to use a technique called EPR for that, so electroparamagnetic resonance. So it kind of looks at the free electrons and spins and stuff in your system. And we just didn't have access to it. There was one person that we thought of that we could have collaborated with, but we kind of wanted to get it out fast, and we weren't sure if it would even work with our system anyway, because it was quite a complex system. So I asked ChatGPT, and it was like, oh, you can use this radical probe. And it's just a molecule that you put into your system. It will react with the radical and become luminescent. And then you can do fluorescence spectroscopy, and you can prove that the radical has interacted with that thing. And that was it. So we just did it in 4 different conditions, and reviewer was happy, and it got published. So it saved a lot of hassle trying to track down collaborators, and if our system even worked in the first place with that, you know. So it was great. Yeah, it was awesome.
That is so cool. So this is a great example, I think, of how AI, or in this case ChatGPT, and human brain work together, collaborate in the best way possible to answer a scientific question. This is amazing. This is exactly what the AI ChatGPT is supposed to do. I'm so amazed. Did you tell the reviewer that this was from ChatGPT?
No, because I performed the experiment and everything. So I reference the papers that, so when ChatGPT was like, you could try this, I looked up a couple of different papers, found papers that had done that technique, and then referenced those. Because ChatGPT can't give you references. So it was like, you can just do this. And I was like, I wonder if that's actually true or not, or if it's, because sometimes when you ask ChatGPT for anything to do with experiments, it's just like, yeah, just throw all this stuff together and see what happens. And sometimes there's elements that are in your product that aren't even in any of your starting materials, and it can be a bit wild sometimes. So I double checked it, and it was actually valid. I found a good few papers to support it, and then did the experiment myself based on the experimentals that were in those papers. Because even though ChatGPT was like, do this, it didn't give you any specifics on how to do it. It was basically like, this molecule can be a probe, so just add that to your system. But it didn't say how much, it didn't say what conditions. So I did need to look for papers to support that. Yeah.
Okay, so whatever ChatGPT or any other AI system comes up with, all the scientists who are listening, make sure you validate it, you cross-check it, you double, triple, 10 times check it, and find the correct, authentic references to support ChatGPT's claims or suggestions or ideas or whatsoever, because this is very important. This is so cool. I can already imagine a conference sooner rather than later that says the best ways to use AI as a researcher, or ethical ways, or ChatGPT wrote this paper, or whatever XYZ. This is so cool.
Yeah, it's definitely something that's going to be used a lot more in the future. I was even yesterday, I was at an outreach symposium that the School of Chemistry runs every year for kind of first and second year PhD students, and one of them wrote an entire chemistry book, but they got ChatGPT to write it, and they were like posting on Instagram and seeing how effective it can be as an educational tool. And like, there was a lot of human editing required, you know, some of the stuff wasn't correct, but it was just to kind of see how advanced it is, and if it can be used for educational purposes and stuff. If you can use it instead of a textbook in certain circumstances, then that would be great, but it's definitely not at that stage yet at all.
Also, it's outdated, right? The last time it was updated,
2019, I think, is
something like that.
ChatGPT, and then I think the Google one is real time, as far as I'm aware. So that is consistently updated. But
exactly, the Google one is real time, but we in Europe do not have access to it yet because of good reasons, valid reasons. But I can't wait to get my hands on the Google one and then compare. Oh my God, the possibilities are endless, literally. Oh my God. Okay, bringing the conversation back to you, Áine. It's clear to me that you love the research aspect of being a materials chemist, but what else do you like about being a scientist? Other than the research itself, what else do you like?
I really like kind of engaging with the public about science, because I think that's something that is kind of a necessity, but people don't see it as that. Like, it kind of is our duty to be able to talk to the public about what we do, but very often that just doesn't happen. So that's how you get crazy headlines about chocolate cures cancer or something like that, and then you read the paper, and the paper very clearly states like, no, it doesn't, we just tested it. So I think that's kind of a side that I really like, that I've leaned into a lot more in the PhD. So I do a lot of public outreach with a team in Trinity called Current Chemistry Investigators, which they go around schools all around the country and different public events and teach them about kind of green energy sources, electrochemistry and that kind of thing. So it's kind of outside my field, but it's still nice to kind of chat to the public about chemistry in general. And then if they're more interested, they kind of ask you about your research and you can kind of talk about that as well. So that's a side that I really like, and it leans into your actual PhD skills so much as well, because it helps your presentation skills hugely, because all of a sudden you have a 5-year-old being like, what do you do in the lab every day? And you're like, oh my God, how am I supposed to explain this to a 5-year-old? And then it helps you then if you're at a conference and there's someone from completely outside your field, they ask you a question that you think is so obvious, but you're like, I've never asked myself that question before. So I think outreach really helps with that. And that's a side that I love. Yeah.
That's so cool. I totally relate to that. And you're absolutely right. The outreach aspect, especially with kids, I think, because they ask you these questions, which are like, why are you asking that question? Where is that coming from? Oh, but that makes a lot of sense. Don't ask me this question. No, do ask me this question. But, oh my God, I should have thought about it 2 years ago or something like that.
Yeah, when they're coming at it with a completely like open and blank kind of mind, they're so curious and they'll ask such crazy questions that sometimes you're like, oh yeah, I should have tried that, or I should have done that. And you're 5, like, you know, it's crazy. But it's awesome though. It's awesome to chat to kids about science and see kind of what ideas they come up with and stuff. It's pretty cool.
Absolutely. And I love to see whatever information I give them, they process it, and the spark in their eyes and the excitement on their face. I'm like, yes, that's
you can see it click at some point, and that's always just so nice. Of like, they're like, I don't know, and then oh, I get it now. It's so like gratifying when you're explaining it and they get it. It's so cute. Like, I love that.
Yeah, it's amazing. I love it. It's very nice. So a bit away from the kids and the outreach. I hope your research experience so far has been wonderful and will continue to be wonderful in the future, thanks to the Irish funding agency, whatever, but money is not everything. If you had 3 wishes to improve your research experience, what would you ask for? And I'm not promising anything here, okay?
3 wishes, only 3.
Sorry.
I think a lot of them are kind of tied into each other, and a lot of it is kind of to do with how research is kind of, how seriously it's taken in Ireland on a general kind of level, on a national level, on a government level. I think Ireland has, you know, kind of punched above its weight quite a lot in terms of research, specifically in materials scientists. We have 2 or 3 scientists, we've specifically Valeria Nicolosi and Jonathan Coleman, who consistently rank upon the top 100 material scientists in the world. They're amazing. But the funding that we get it's not indicative of what we actually do. Like, we definitely punch above our weight in terms of what we get. And it's to do with how seriously the government kind of take research. So there's been plenty of reports showing how beneficial research is for not just society, but also economy, because that's what the government are thinking. How can we, keep it afloat, make money? And a recent report said that one of the nanoscience research centres in Ireland, in Cran, they roughly produce €10 for every euro funding they get. They roughly pump €10 back into the economy, so which is an amazing percentage, right? But we're still one of the most underfunded countries in the EU. So I think the EU recommends spending roughly 3% of its GDP on research, and Ireland spends less than 1%. So we are kind of chronically underfunded in this country. And also, so that's kind of on a general level. So like individual groups and stuff not getting funding, but also we don't have any kind of workers or employee rights as PhD students. We're just treated like an undergraduate student in terms of our rights, but you're expected to teach and do a lot of work for the university, not just your research, but teaching and correcting exams and supervision of students and everything. And depending on the university you're in, the department you're in, you don't always get paid for that. You just have to do it. It's part of your contract, even though our contract isn't a work contract. So it's there's a lot that I would change. They're all kind of, there's probably 15 wishes in there, but they're all kind of tied into each other, you know? And I think it's just, changes is kind of coming. The government recently did a massive review into PhD supports in terms of, bereavement leave, maternity leave, various workers' rights, visa issues for international students is a massive one, of course. They have to reapply every single year, even though they're there for 4 years. It makes no sense. So there is change coming. There was a massive review done, and the report is due out hopefully at the end of this month. And there should be some recommendations in there for increasing pay. And I don't think we will be granted worker status, but we may be given some more rights that kind of align us almost as employees, but they don't want to define us as an employee because they think that's kind of a legal gray area. So we stay as students, but they hopefully going to give us some more rights that we're almost kind of workers, even though we are obviously workers. But yeah, it's a bit of a mess in Ireland, kind of academic landscape at the moment, and a lot of people are leaving. And the idea behind this review is to try and retain the talent that they already have, rather than having to attract so much from abroad, that there is already people here, people that have come from abroad that want to stay here, that can't stay here. So then they have to go back home or go to different countries to, do postdocs, whatever they want to do. So yeah, it's a bit of a rough area at the moment in Ireland, but I think change is coming, and I think it should be good.
It should be. Yeah, fingers crossed, definitely. That's very interesting. I always thought that, Trinity College Dublin, I read so many papers from Trinity. I read so many papers from UCD, from PCD. I read so many papers from Ireland, Irish, let's say, research institutions or universities. And in my head, it was like, yeah, perfect. Ireland has lots of money. In research, specifically research, that would be a great place for me to do a PhD or a postdoc. But the reality is completely different. That's very, very interesting. Oh, wow.
Yeah, the reality is like, yeah, we're getting the output out, but we're doing it on equipment that's 15 years old. You know what I mean? So it's like when I was talking about one of the machines earlier, that I love the technique, but I don't love our machine. She is basically just a mixture of 3 different machines of some of the parts were working, and they kind of just made a Franken machine. And that's what we have to do. Like, our technicians do way too much work. They have to fix so much equipment, just because the money isn't there for updating the infrastructure and for maintaining service contracts and stuff. That's kind of the main issue of that. There isn't those kind of pools of money set aside for universities to maintain the equipment that they already have.
And what is the government's reasoning behind only spending 1% when the EU says 3% of your GDP should be spent on research?
It's kind of always put aside of like, no, we spend, and they'll just like give the figure of like, oh, we spent 200 million or 300 million or whatever in this amount of months. And I'm like, yeah, but it's still, we're making, as an economy, we have this much money, so we should be investing more. It's always kind of, the question's always avoided one way or another of like, we're spending enough, and look at our output, we're still, performing well on the international stage, but then you see the university rankings and we're slowly dropping because there's not enough academics staying. So the like student to teacher ratio is way higher. So that like falls you down the rankings as well. And then in terms of your funding and stuff, that affects it too. So we are seeing the effects of the underspending on research, but they're just like, I'm just not going to look at that, maybe.
It's not my problem. Because in my term, I'm not going to see, these are long-term effects. These decay or deterioration is a long-term effect. I will be out of the office by the time this happens, so that it can be blamed on the person who is currently in the office. This is this typical political shit show. Yes. But I had heard, what I had heard about Ireland, or the funding of the research in Ireland, especially materials and nanoscience, is that the funding agency in Ireland requires scientists to have a science communication work package within the project. That's why there are lots of, like, all the researchers have to communicate science, be it on social media, be it at conferences, public, whatsoever. Is this true, or is this a myth?
Yeah. So I think when I started, I'm not sure if it is mandated now. I think when I started it wasn't, so I don't think it applies to me. I think it kind of applied for the year after me. Now, if it was mandated, I would definitely like fulfilled my quota if there was a quota. But my supervisor does ask roughly like every 6 months. He'll like ask everyone in the group of what outreach they've done, and he'll compile a list. So I presume he's the one that has to kind of give it to the agency to say that they've, done this many hours. Like the requirement is very low. It's like a couple of hours a year. It's not a lot. It's really not a lot. It's very easy to do. But they are, I think, a bit more stringent in what you have to do. So I don't think posting online counts. You know what I mean? I think you would have to, I think a podcast, I know one girl did a podcast, her and her friends kind of set up like a 3-episode kind of mini series. And that counted. But I think like posting on Twitter about like, what you do, that doesn't count because they can't track hours and stuff. So I think it's more going to schools or going to public events. But because it's not mandated in my contract, I'm not 100% sure what the actual rules are around it. But there is a rule for both Science Foundation Ireland and the Irish Research Council. So they're the two main funding bodies in Ireland that are actually now merging to become one next year. So yeah.
Okay, interesting. That is very interesting. How about this? After your week on Real Scientist Nano on Twitter, I give you the stats as to the number of impressions your tweets had, or the click-through rates or whatever. Because this is impact, right? This is
absolutely, yeah.
So let me get back to you with those numbers. Do remind me if I forget. And speaking of Real Scientist Nano, you will be tweeting from the Real Scientist Nano account very, very soon. So what can the followers, so far we have 3,200 followers. That's a lot of people. What can the followers expect in the week that you're taking over the account?
So I think kind of initially it'll be kind of a bit more chill, just like introducing myself. I'll probably introduce some other members of the group as well, because our group is really diverse in terms of backgrounds and in terms of research that we do. There's a crazy broad amount of research done in that group, and it's all really cool. So I think I'll probably introduce, other members of the group as well as myself, and kind of the areas that we work in, a couple of kind of key papers. And then I think throughout the week, I'll focus on other areas or other papers kind of in my area that I find really cool, that I've come across, that I'm like, to highlight other authors and other scientists as well, of like, that they're killing it in their field, you know what I mean? So I think I want to do a lot of that, of like highlighting and promoting other research as well that might not be promoted as much. Like they might only have, 50 followers on Twitter, so they post it on Twitter and no one sees it, that kind of thing.
Right.
And then I think I would like to kind of highlight the research landscape in Ireland a little bit as well, give people an idea of what's going on here, the changes that are coming, hopefully. And then I think the 2nd of July is my last day on the Twitter account. And on the 3rd of July, I'm actually going to a conference. So I'm probably going to highlight that conference a little bit. It's in Dublin, and it's the RSC's International Conference on Materials Chemistry. There's a lot of cool speakers. So I'll probably highlight that a little bit as well towards the end of the week, because they do have an online option for registration as well. So you don't need to be there in person.
Oh, that is amazing. If you want to stay for one more week and give us a sneak peek into the live tweeting, all for it. Absolutely. If let's talk about it after this.
Yeah, absolutely.
Oh, that sounds so cool. Oh my God. Áine, it was so nice to speak with you. I learned so many new things, and oh my God. Thank you very much for adding to my knowledge pool, and very, very excited to have you on Real Scientist Nano. Super amazing research you have, and you are awesome. So thank you very much.
Thanks so much for having me. It's been great. It's been really nice chatting to you.